Hello everyone, this is Mandeep Singh Shekhawat and today I'm back with another video where we'll be discussing QALM. Okay, so QALM is basically Uber's architecture to resolve load shedding. Okay, when I say load shedding is basically means if there is some unwanted load on the system, how can you shed it, how can you remove it, how can you drop it. So shedding basically means if there are some, you can say, the requests are always useful, but in case of high load on the system, let's say my system is experiencing unexpected load, okay, and my system is not designed, or I don't have that capacity right now to handle that much of load. So in that case, some of the requests are dropped, shredded. So that we will be discussing today, how Uber designed their QALM architecture. QALM is basically QAS aware load management. So let's go into the architectural details. And before that, if you are not aware and if you have not heard about my upcoming book, which is System Design on AWS, do check it out. You can find right now this book on O'Reilly platform. You can read it and share your feedback on LinkedIn, or like any of the mechanisms you can directly write an email, so all those things. But yeah, great book to learn system design, architecting systems on AWS, as well as how can you come up with the generic design systems overall. Cool. So let's get started with our architecture, in which we will be discussing first what is the requirement. Once we are clear with the requirements, and definitely it applies to all the systems we design, right? You have to first figure out the requirements, and once we are clear with the requirements, then we will go ahead doing other stuff. Whenever I say other stuff, it's basically design. So I mentioned that QALM, right? So a, a weird name, but yeah, it's a QoS aware load manager system, and QoS means quality of service. Okay, so QoS aware basically means that whenever a quality of system is degraded, so in that case, uh, basically you have to ensure that quality is not degraded. Okay, so to ensure that, some of the requests are dropped, and there is, I'm not sure who said it, but the idea is that either you can decide to serve some of the customers, okay, or you can decide to serve not none of them. Okay, so it is highly improbable scenario that you will be able to serve all the customers at all the time. You will have like lot of strategy in place, which will ensure that your system is working always, but there can be scenarios, so it will be a difficult feat to achieve, right? Difficult feat to achieve that your system is 100% available. Okay, so if that's not available, that's not happening, so how can you gracefully degrade it? So that's what we will be discussing today. So on the requirement front, what do we want? When we need dynamic load shedding framework. When I say dynamic, it means that I'm not defining any too many of configurations. Some of the configurations we will be defining, but not too many of them, and it should be automatically adjusted. Okay, so it should not happen that at time of, let's say, the load has increased, so go and uh, probably drop the some request by your own. Or let's say, when I say configurations, you might have defined a queue in which the request comes in, and till a certain threshold, if the requests breaches that threshold, then requests are dropped. Okay, now that request rate, the system, like at the rate which system is processing the request, can also vary, right? So to address those scenarios, dynamic nature is very important. Dynamic nature is very important, so that as per the load, or like how many requests the system is currently pursuing, or what is the time taken by the each request to be processed, all those things can be taken into account, and our system can accordingly drop the request, like the number of requests. It can figure out that these are the number of requests that should be dropped. And definitely other thing is like on the depending on the criticality of the request, right? So let's say at this point of time, if there are any batch requests, or like offline jobs, or let's say some internal use cases calls from the dashboards and all, so those requests can be treated as non-critical and directly customer request, let's say right booking request. So those are the most critical request for me. Okay, if I'm not allowing the users to book their rights, so I'm not doing the my base operation. Basically, Uber as a base operation is that you allow users to ride a book a ride. Cool. So that is my most important critical requirement, and it should be solved. Intelligent overload detection, again it's similar to that what I already described, that our system should be able to do it automatically, and we should not jump into it again and again, that yeah, tune these configurations. It should work automatically out of the box. Request criticality registration. Now when I say registration, so by the way, like this is the architecture from the 2018, and there is a improved architecture Cinnamon, which Uber recently published. So we will discuss that in the upcoming videos. But this is important because like this is the improvement per se to start with. Okay, from like they had nothing earlier, and like each team has to manage their own load setting frameworks. So this was the one step further. Then after 4 years or 5 years, we had another improvement, which is the Cinnamon, which we will be discussing in the upcoming videos. So in this video specifically, we will be discussing QALM, and in the next video we will be discussing Cinnamon and what were the issues with this QALM. Cool. So let's get started. uh, it's not a good sign to say that yeah, there will be limitations with this system, but yeah, like none of the system is perfect and there are always limitations, but yeah. So request criticality registration means, let's say I have multiple clients. Okay, so if we take an example, let's say I have multiple clients, service A, service A, service, I mean, so take uh, uh, think of in this direction, that I own a service. Okay, so it's a Mandeep service. Okay, Mandeep service, and service A and service B are my clients. So service A and service B invokes some of the APIs of Mandeep service, and Mandeep service has multiple APIs. Okay, and so for now it says two APIs, API 1 and API 2. So service A uses two of the APIs, API 1 and API 2, and service B uses API 1. Now it is a highly possible scenario that for service A, API 1 is highly critical, but for service B, it's not. Okay, so that's what we mean by registration. Okay, criticality registration. So the criticality registration should be done as part of onboarding architecture or onboarding systems. That there is a chair in my background, another chair, but yeah. Where were we? So our system should be able to do that. So it's like multi-tenant system kind of thing. Cool. Endpoint isolation. So when I say endpoint isolation means like one endpoint, or endpoint basically means your API. Okay, endpoint basically means your API. So one API should not be impacted by another API. So if there is load on one API, it should not impact other APIs, and the load should be dropped on that API, not other APIs. So they should be handled separately, or there should be isolation in place for them. Great. Now we are clear with the requirements, so let's go ahead and think on the design. So it's all based on the blog, which is this, introducing QALM, Uber's QaOS load management framework. And this is a great diagram. I have added this in the notes as well, so we will discuss there. But yeah, this is the blog. If you want to read away, I will share this link with you in the video description, and you can check it out. And our video definitely has a great summary, so you don't need to. But yeah, if you like reading, go ahead and read it. So back to the design. So in our design, in the requirement sections, we mentioned some of the requirements, right? We need dynamic load setting, we need intelligent overload detection, we need request criticality registration, we need endpoint isolation, intelligent overload detection. So what we need there? So I mentioned that we need a dynamic nature of configuration. Now, why do we need that? Because in case of static rate limiting framework, uh, you have to tune your configurations. Okay, and it highly depends on the service capacity, like what kind of instances you are using. Let's say if you are using, in case of AWS context, let's say you're using M4 large. Okay, in that queue size is 100 works best. This is just the examples. Okay, this is not any kind of recommendation, but yeah. And let's say for M4.4x large, 200 works best. So as and when you are changing the instance types, okay, or as and when you are increasing the number of instances, your configurations change. Okay, so this change of configurations is very hard to manage. Cool. And if let's say this is a platform service, so a lot of the clients will come in to onboard their systems, okay, and then use this. So it becomes hard to manage them. So that's where we need a dynamic. And dynamic overloader, one of the algorithm is Codel algorithm. Codel basically means controlled delay. We will quickly discuss this, what Codel means. There is a nice Wikipedia article which describes all these steps. We will definitely not go into the code. We will just try to understand how this algorithm works or what is the idea behind this algorithm. So Codel means control delay, and it's basically your queue management algorithm, and it's used heavily in the network systems to avoid congestions. Okay, so take an example of router, okay, and you will be able to relate this much to our use case right now, what we are trying to solve here as well. So take an example of router, and the route on the router there are a lot of requests which are coming in, okay, lot of requests are coming in. Now we have to ensure that the requests are not placed idle. When I say idle, idle basically means वो चुपचाप पड़ी हुई है, कुछ नहीं कर रही. Cool. There is no work assigned to it, okay. So as part of optimizations, we want to ensure as soon as the request comes in, it start processing, okay, it's not waiting in the queue. So how can you reduce that waiting period? How can you reduce that waiting period? Okay, so if the requests are waiting so much, a buffer is created which is called buffer bloat. Okay, buffer bloat, amount of time spent by the packets in the queue. When I say packets in the queue, which means they are not the processing is not beginning. Okay, the request arrived and it's just there, okay, it's just staying there in the queue, processing didn't start. So that's the idea behind this Codel algorithm. You have to, I mean, the idea is that it's a queue management algorithm, and it is used to reduce network latency and improve performance in congested networks. The idea, sorry so much, I'm not sure is the correct keyword, but yeah. Anyway, avoid long queues. Okay, and how can you do that? Codel use delay based drop strategy instead of relying on queue size, which is static configuration. When I say delay based drop strategy, which means is the idea is, let's take this example. Okay, so this is your caller. You sent a request. Okay, I forgot this as a QALM for now. Let's say this, you have a queue right now here. Okay, so you sent a request. Okay, once the request has reached to the service, uh, it will be sent to a particular request handler. Okay, it will, let's say, your REST controller. Cool. uh, so there might be a delay in between. The request has arrived the queue, then it will be picked by a handle. This, the time difference between them, that's where the Codel algorithm shines. Basically, when I say science, is it works on that principle only, that how can you reduce that time frame, and it uses that time frame as its differentiating factor, or your, let's say, your key point in the algorithm to decide if the request has to be dropped or not. So if the requests are staying more than a target latency, more than target latency, then they are dropped. Not target latency, target delay. So that's what we discussed. We avoid static configuration, which is queue size. You don't maintain any queue size. The requests are dropped if you are breaching the target delay. You don't have to define configurations such as queue size, packet drop thresholds. This is automatically adjusted as per the network conditions. Algorithm work based on defined target latency or delay threshold, which we already discussed. On breaching threshold, a packet is dropped. Great. What is delay? Delay is time between request reaching the server and start of actual processing begin, which we already discussed as part of this diagram. Cool. If packets are dropped, Codel sends a congestion signal to sender to reduce sending rate. And this is a great way to inform the sender that there are too many requests and there is a high probability that your request will be dropped, so don't send it. Because anyway they will be dropped, so there is no point you sending the request because we are not serving it right now. So this is what we mean by Codel algorithm, and this is used. There is definitely a modified version of it, but yeah, this the idea of Codel algorithm is used as part of intelligent overload detection in our QALM architecture. You have a request buffer queue, which we already discussed, which maintains the requests. Each queue monitors minimum latency within the sliding time window, trigger overload condition if threshold breach. We already discussed this. Another point is endpoint isolation. Now, one of the requirement was that endpoint isolation. When I say endpoint isolation, API 1 should not be impacted by the operations of API 2. So, all the APIs, all the endpoints should be independent of their load on each of the endpoints should be independent of each other. So each queue has a separate overload detector. Cool. So the queues are maintained at an endpoint level, and each queue has a separate overload detector. Load shedding on one endpoint doesn't impact other endpoints. So quickly take uh, let's clear it from the diagram. So you have consumer 1, consumer 2, consumer 3. Consumer 1 and consumer 2 are hitting endpoint 1 and consumer 3 is hitting endpoint 2. So if there are like 4 XX on consumer 2, okay, it is not impacting the consumer 3. Cool. And that they have definitely their this all things we discussed, right? There is a criticality registry. We have a registration in place so that each of the endpoints, or like each, like as per the service, they are defined that this is the criticality of each of the services. Now coming to the request criticality, we already took this example, right? We already took the example that how it will work. So as of now, as part of QLM architecture, there are 4 levels of criticality: core infra request, they are never dropped; core trip flow request, they are never dropped; user facing feature request, additional enhancement, you might drop them; internal traffic such as testing request, you can definitely drop them if the system is detecting overload. So there is a high probability of removing these requests. This table we already discussed, we took the example of how this helps in the registration. Great. Results, we will go to the blog and see some of the graphs, but before that let's quickly talk around the integration. So we mentioned that we want to develop this as a platform service, right? We want to develop it as a platform service. Now when I say platform service, as part of platform service, right, what you want to ensure is that your client should be able to easily onboard on that system. Okay, your client should be able to easily onboard. Now when I say onboard, what do I mean? One thing is criticality registration. You are doing that. Great. Another thing is how they will use it. Okay, they onboard this as a system? Like, is this QLM as a separate service? Like, do I have to onboard to this service and I have to send the request to this service, or is it some sort of library which can be integrated in the code? So how Uber does it, how Uber did it, not does it, did it, they have, I think they might have removed it right now because in favor of Cinnamon. But yeah, so they have this YARPC framework which is built for Go, and they use it for, and every company has separate. Amazon has Coral, something called as Coral framework. So this is for a Go, this was a Go framework for the RPC. RPC means remote procedure call, basically your REST API calls or any of the calls which you are making to the system. And whenever they are hitting this, so this is part of as your, this will be part of your system itself. So the request will come through this QALM and then they will be redirected to handler. Okay, and if if this QALM framework detects that request should not be served and dropped, in that case it will be dropped. Great. So let's quickly go. I mean, you can definitely check out the results by your own as well. But if you see overall like experiments with the team did graceful degradation, it worked quite well. Cool. If we talk about criticality awareness, these are the improvements which are there in the graphs, and this we already discussed how, like, how it was made available to the clients so that they can easily integrate with the QLM, and there is not much of the what do you say, engineering effort required to for the integration per se to get benefits of this library. Uh, these are again graphs how it helped in reducing those loads and like dropping the requests, right? So another thing is, just to summarize on whatever we discussed right now. So we mentioned that it is a platform service, and there are some of the recommendations which are added as part of this blog, and they are definitely useful if you as well is developing some of these architectures, right? If you see that your service will be used by multiple clients, so first thing you have to ensure is that your integration should be seamless. There is like very less churn involved when they are integrating, when the other teams, other engineers from the teams are integrating to your service. So documentation should be great. uh, as part of documentation, you should provide like what does the API look like. You should share some sample request, how they can test it. So all those things, documentation should be great if you want to ensure that they are able to self onboard. And as far as possible, you should provide all the APIs. So for let's say for criticality registration, they can, you can ask them, let's say on a particular ticket that give us, and then we will configure them in the database. That's again extra churn, right? They have to raise a request, and then your engineer or your on call has to take that effort. But you can remove that if you provide directly the API. So they can, at future point of time, if they want to update that criticality as well, they can do it easily. So documentation should be great. You should provide for simple operation, you should provide APIs for simple operations as well. Proper metrics should be in place, okay, for your system. And your you if your system is a platform service, right, you should be able to identify what systems are, let's say I have my 5 clients. Let's take this example. I have my 5 clients, and if any of the client is not behaving properly, okay, other 4 clients should not be impacted. Okay, we discussed this in one of the architecture of endpoint, one of the design principles in this is itself of endpoint isolation. Like this was one of the requirement. So as part of endpoint isolation, one of the API is not impacted by the other APIs. Similar goes for the multi-tenant system, like operations of one client, operations of one service to your architecture. And this is QLM is library, but this is more favorable or more useful advice in terms of service. But the idea is that if there are multiple services which are calling to your system, one system or one service operation should not impact the operations of other services. So you might have rate limiting in place for all the services, like you define that this is the TPS which is allowed for a particular service, and this is what it can hit. It should not happen that all the requests are, all the capacity of a service is used by one client and their clients are just hanging around. Okay, so this is one thing, metric should be there, proper documentation should be there. Another thing is, uh, this is a reliability logic. I mean, we are trying to improve the reliability of our services, right? So this is a reliability logic. So what you want to ensure is that it should not be mixed with a business logic. There is a lot of business logic which is written, there is a lot of business logic which is written uh, as part of your service. So it should not, it should be a separate module. Okay, uh, to start with, you don't have to create a separate service or separate repository in Git. You can just create a separate module in your code and then use it, so that in future if it needs to be extracted out, it can be done. So this is all for today's video. We will be back. I will be back with another video where we will be discussing another engineering blocks, great engineering blocks, great insights. Till then, stay safe. Tata. Bye bye.